Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're in chapter 8, which deals with water movements. And more specifically today, we'll be looking at turbulence in lakes and ponds. Eddy diffusivities in lakes vary over predictable ranges in the upper mixed layer, the thermocline and the hypolimnion. The highest eddy diffusivity may be in the order of 10 to the minus 2 meters squared per second in the upper mixed layer on a windy day. The values of Kz may approach molecular values of 10 to the minus 9 meter squared per second for solutes and 1.4 by 10 to the minus 7 meters squared per second for heat. Spreading in the horizontal is much faster than in the vertical in lakes, with initial scaling indicating spreading in the horizontal would be proportional to the patch size L raised to the 4/3 power, that is L to the 4/3. Let's see. Ecological importance of KH and KZ. Quantifying KH and KZ is of considerable ecological and biogeochemical importance when concentration gradients of solutes or particles such as algae or sediments occur. Fluxes can be calculated as described in equation 810. Kx and Ky are usually horizontal dispersion coefficient in the x and y direction, and Kz is the coefficient of eddy diffusivity in the vertical direction. In the vertical, this equation implies calculating the flux of solute in units of moles or mass across a plane into a series of volumes over a defined time, and then by accounting for the changes in moles or mass in each volume, determining the change in concentration in each volume per unit time. To determine how the concentration of a solute C changes with time due to both advection and diffusion, an advection-diffusion equation is useful and is the basis of many numerical models of hydrodynamics. So I'll let you look at that here. Timescale approaches. While expressions such as equation 18 are complex and made more so by adding the reaction terms, scaling arguments are often used to simplify analysis. They can determine, for instance, how fast the transport would be and then can be evaluated against the timescale of biological or chemical processes. Okay, there's some more stuff here. Small scales in turbulence. The attributes of turbulent eddies on the smallest scale, the Kolmogorov microscales of length, time, and velocity, can be computed from the rate of dissipation of turbulent kinetic energy, sigma, and kinetic viscosity, V. The Kolmogorov microscales are used in models to quantify fluxes at the benthic and atmospheric boundaries. Okay, so we went over that. Dissipation rates tend to be lower near the benthic boundary layer. However, for the dissipation rates above and for dissolved oxygen at 25 degrees C, LB would range from 110 to the minus 4 meters to 2 by 10 to the minus 5 meters at the benthic boundary layer. This calculation illustrates that as turbulence increases, the viscous sublayer and diffusive sublayer progressively thin, with the potential for enhanced fluxes across interfaces. Phytoplankton, bacteria and other microorganisms tend to be smaller than the Kolmogorov microscale, and hence are embedded within these eddies. The diffusive boundary layer around a phytoplankton cell is about 10 times larger than its radius. Thus, for phytoplankton cells that range in size from 1 micrometer to 100 micrometers, the diffusivity boundary layer would range from 110 to the minus 5 meter by 110 to the minus 3 meter, such that in most cases, the layer is smaller than or equal to n, and thus itself will not become turbulent. Instead, the boundary layer can be deformed by the turbulence in the flow. For appreciably larger phytoplankton, or those in colonial form, greater than 400 micrometers, the boundary layer thickness would exceed n. However, very little energy is contained in turbulent eddies, even 5 times larger than n. Hence, that diffusivity boundary layer is not expected to become turbulent. For larger algal cells, however, including colonial and filamentous morphotypes, there is an increased capacity to take up nutrients relative to being in stationary flow. The increased uptake points toward thinning of the boundary layer by the shear and pressure fluctuation of the small eddies, enabling the more rapid uptake. A challenge for phytoplankton is to remain in the euphotic zone where there is adequate light to support growth. Diverse strategies have developed, including being positively buoyant, neutrally buoyant, or having flagella. Some algae, like diatoms, are negatively buoyant, that is denser than ambient water. The sinking floating velocity of negatively, positively buoyant phytoplankton is derived from the Stokes law. Okay? In laboratory experiments, the sinking speed of growing phytoplankton are generally less than those of senescent cells, and both growing and senescent cells have sinking rates lower than those predicted by Stokes' law. Various morphological adaptations lead to sinking or floating speeds differing from those predicted by Stokes' law. Similarly, accumulation of lipids may reduce the density of, or for example, diatom and slow their sinking speeds. Even positively buoyant phytoplanktons may have evolved strategies to improve their competitive success. Accumulation of lipids can make colonies of the chlorophyte Brotiococcus browni even more buoyant. Understanding many aspects of aquatic life as well as biogeochemical transformation requires knowledge of turbulence. The small-scale velocity fluctuation associated with the eddies in which cells are embedded will cause subtle changes in their position. Somewhat larger eddies will potentially sweep them away from grazers, and even larger eddies will act to redistribute them, modify their residence time in the water column, and expose them to fluctuating light. Thus, turbulent eddies at a range of scales, with the smallest motion being a lifetime of 10 to the minus 3 by 10 to the 3 seconds, modify the growth of phytoplankton and influence organisms of different sizes in lakes and flowing water. Water movements in rivers and streams. Principles of open channel flow. In rivers and streams, the stream banks and bottom constrain flow to a channel that is in contact with the atmosphere. The flow in the channel is called open channel flow. Changes in water pressure in the stream from incoming or outgoing water lead to increases or decreases in water depth because the relative change in atmospheric pressure is negligible. Gravitational forces that induce water movement depend on the bottom slope and oppose the frictional forces acting to the stream bed and bank that impede the flow. The flow in streams is mostly turbulent, driven by channel bed slope, and modified by the stream morphology denoted as the characteristic length scale L or hydraulic radius RH. As stream velocity decreases, for example in downstream region where slope decreases and stream depth and width are usually increased, the flow becomes less turbulent. Stream velocity of mu or meters per second can be described by by the Gauquelin-Manning formula, usually referred to as a Manning equation, where n is Manning's n, which is dependent on the depth and characteristic of the stream bed that alter frictions, including the nature of the substrate, the stream bank morphology, and presence of vegetation. A guide for selecting Manning n values for natural stream channels and floodplains is given by R. Semant and Schneider, but there will be some variations among stream outreaches with flow conditions and with stream sinuosity not accounted for in the guide. So this is riffles in an Austrian stream create high levels of turbulence that ensure rapid dispersion and homogeneity of the bulk water within the streams. Pools are downstream, denoted by smoother areas of the water surface. So here are the pools, here we have riffles. And then here is an example of turbulent flow at the Rhine Falls, where the water depth is highly variable. Flow regimes in streams and rivers can be characterized by dimensionless Froude number that considers the ratio of inertial disturbing force given by the water velocity to the opposing gravitational weight of water based on the hydraulic mean depth. Okay, so here's the equation for the Froude number. Froude number is important for defining flow regimes. When U varies little at a point under base flow condition, the flow is characterized as steady as opposed to unsteady flow with large fluctuation in velocity. Hence, base flow refers to residual stream flow, mostly associated with groundwater input to the stream and stable in the short term, with gradual changes at longer time scales. Corresponding to fluctuation in groundwater levels and more abrupt changes that lead to velocities above base flow associated with rainfall. Values of FR less than 1 correspond to subcritical flow when gravity waves disturb the uniformity of downstream flow, denoting, for example, by surging and backflows at the edges of a stream channel. The speed that an individual wave propagates is wave celerity, represented by the square root of GHM in the denominator of the Froude number. Supercritical flow, FR greater than 1, means that these waves do not disturb the continuity and uniformity of stream flow, downstream flow. Various other classifications are in use, including turbulent and laminar stream flow, which are differentiated by the critical Reynolds number. Between the two is a range of RE values corresponding to transitional flows. The variability of flow along a stream provides a diversity of animals, often associated with longitudinally with runs, riffles, and pools, and literally with the Thalberg, deepest part of the channel, main channel, and the shear zone separating it from the quiescent nearshore region. Hydrographs. The volume of water per unit time passing a point is known as discharge or flow rate, in meter cube per second. It can be visualized as the discharge of flow speed and cross-sectional area. Discharge varies by location and time, with notable increases during storms. A hydrograph is a plot of Q as a function of time, t, for a fixed location. Base flow occurs when flow is steady, for example, 1 meter cubed per second. In figure 8-13, whereas storm flow, also known as quick flow, is characterized by changes, figure 8-13. For example, the rising limb of the hydrograph occurs when overland surface runoff and shallow groundwater flow increase with rainfall. The duration of storm flow depends on the intensity of rainfall and the relative contribution of surface runoff and shallow and deep groundwater, with the offset being the peak of rainfall and the peak of stream discharge reflecting storm intensity and the relative contribution of surface and groundwater sources. A recession limb follows the peak discharge when rainfall in temporary storage, mostly shallow groundwater, is gradually depleted and the discharge decreases toward base flow. So let's look at figure 8-13 here. So hydrograph showing base flow and storm flow discharge, blue line. This is for Utuyana stream in Rotorua, New Zealand, and rainfall at Wakarewa station within the catchment. So let's see. So we have, I believe this is rainfall, and this is in millimeters. This is the discharge in meter cube per second, and these are the dates. So what we are looking at is we are looking at base flow right here, or right here, or right here, like reestablishment of base flow. Right, we're looking at rainfall. So there's like a rainfall event. So there was a pretty quick reaction of the flow in the river following the rainfall. And you can see, like, for example, when we have like even like some amount of rainfall, there's a response. Here, however, we saw just a very small little response, even though that is the same amount of rain that fell here. So for some reason, we didn't see that response. And then the transition flow. So this is the peak flow right here, and the peak flow right here. The transition flow would be like right around here. And let's see here, figure 8-14, flow duration curve, mean daily flow for the subtropical ephemeral Condamine River at Yarramalong Weir in Queensland, Australia, from 2019 to, from 1989 to 2016. The river is dry for more than 1/4 of the time, i.e. discharge is not detectable. They don't live at the horizontal baseline. So this is the horizontal baseline, and this is base flow. And this is the response to a rainfall event. This is the discharge in meter cube per second, and this is an exceedance probability. Let's see. Median daily flow is 0.09 meter cube per second, and sun flow for the summer wet season can exceed 100 meter cube per second. So let's see. So they're telling us, like, this is a flow duration curve. So I mean, in terms of like time, I don't see like a time-based value here. I just see like a probability against discharge in meter cube. Let's see. The shapes of hydrographs vary spatially as well as temporally. Based on factors such as land use and land cover, which affect the balance of rainfall and evapotranspiration. Soil infiltration capacity affected by soil composition and extent of impervious surface, the size of the unsaturated vadose zone and the saturated phreatic groundwater zone, slope which affects the rate of water delivery, and the rate of snowmelt in regions with seasonal snow cover. Hydrographs differ within a stream depending on discharge and distance from the headwaters. High in the catchments, streams are classified as lower order and away from the headwaters. Streams that are usually classified as high order, for example, in the Strattler system, headwater streams are denoted as first order, and as streams join, the resulting stream reach has the same order as the higher value of the two joining stream reaches. Hydrographs of lower order streams have relatively steep gradients in the rising and recession limbs compared with the higher order part of the stream network. Where groundwater is strongly depleted, for example, seasonally in Mediterranean climates or with high levels of extraction, base flow declines to zero, leading to an intermittent stream or a perennial stream that dries out. These processes indicate the importance of base flow in maintaining key stream ecosystem processes and habitat for biota, as well as for providing water supply for humans. The frequency of flow of a given magnitude generally involves the application of a flow duration curve, which relates flow on a logarithmic scale to a percentage or frequency of exceedance. Flow duration curves are useful for consideration of the median daily flow 50% probability and derivation of the probability of extreme events, for example 1% in 1 in 100 years and 10% 1 in 10 years, that inform the design of flood control measures. These probabilities are strictly applicable only to the instrumental period, and their direct application to a future period assumes stationary or rainfall runoff, including for periods under the influence of climate change. So here what they're telling us is, for example, like we have like 10%, so 10% probability, that would be like one event every 10 years of having a flow of about like, let's say 9 cubic meters per second for this river here in Queensland. And then let's say like we had like, so then we have like 1% in 100 years. So 1% would be like, put us right here. So 1% in 100 years of having about like 70 meter cube per second. So that's pretty rare. So, and then this is the base flow that happens between like 75% and 100%, of course. So I think that's going to be it for today, and we'll see you tomorrow to go over exchanges at boundaries. Thank you for your attention, and looking forward to it, and talk to you soon. Bye.